In the quiet autumn of 1967, in the hushed, almost monastic confines of Cambridge University's Mullard Radio Astronomy Observatory, a revolution was brewing not in a grand theory, but within a few fleeting blips on a paper chart. This was not the kind of discovery anyone anticipated. It began not with the majestic collapse of a star, nor the violent birth of a cosmic titan, but with a persistent, almost irritating speck of noise, a scruff, as it was dismissively labeled by some. For Jocelyn Bell Burnell, a diligent postgraduate student, this scruff was more than just interference. It was a rhythmic, repeating pulse of radio waves, arriving with a regularity that defied explanation, a cosmic heartbeat echoing through the vastness of space. She and her supervisor, Anthony Hewish, had designed and built the immense interplanetary scintillation array, a cutting-edge instrument for its time, sprawling across 4.5 acres, its 2,048 antennae meticulously strung on hundreds of posts. Its primary mission was to study quasars, distant, energetic objects whose radio signals twinkled due to solar wind. Yet, the very sensitivity designed to detect these subtle variations led them to something far more bizarre, an object that, according to the stellar physics of the day, should not exist. The signal, designated CP-1919, was unlike anything seen before. It pulsed with an almost perfect period of just over 1.3 seconds, an unfathomable precision that rivaled and even surpassed the most accurate man-made clocks of the era. How could something in the depths of space, a natural phenomenon, broadcast with such metronomic accuracy? The initial scientific response was skepticism, bordering on disbelief. Bell Burnell embarked on a relentless campaign of cosmic detective work, meticulously cross-checking every possibility. Could it be terrestrial interference, perhaps a rogue military radar, or a faulty piece of equipment? No, the signal's origin clearly lay beyond Earth's atmosphere. Could it be a satellite? Its precise, unvarying period ruled that out too. As the weeks turned into months and the signal stubbornly refused to disappear or vary, the mystery deepened. In the intellectual climate of the Cold War, a period where the search for extraterrestrial intelligence was quietly transitioning from the realm of science fiction to a nascent scientific field, a playful yet undeniably serious hypothesis began to circulate within the Cambridge team. They half-jokingly, half-earnestly, dubbed the source of these unbelievably regular pulses Little Green Men 1, or LGM-1. It was a radical thought, a signal so precise, so artificial seeming, that it genuinely led some of the brightest minds to consider the possibility of an intelligent alien beacon. This enigmatic scruff, this ghostly whisper from the cosmos, was a direct challenge to humanity's understanding of the universe. Here was a stellar corpse, an object that had long ceased the fiery nuclear fusion that powered its life, yet it was sending out a message with a clockwork regularity that seemed to defy the very laws of physics as they were then understood. It was a paradox that demanded an answer, forcing scientists to confront the limits of their knowledge, pushing them to conceive of something truly unprecedented. This was the moment astronomy stumbled upon an anomaly so profound it would rewrite the rules of cosmic death, revealing objects far stranger and more powerful than anyone could have imagined. In the early 1930s, a new particle had just shattered the known universe. James Chadwick, in 1932, confirmed the existence of the neutron, a subatomic enigma with no electrical charge, nestled deep within the atomic nucleus. This revelation was a seismic shift in physics, but few could have predicted how quickly two audacious minds would wield this newfound knowledge to prophesy the very architecture of cosmic death. This was not the era of tantalizing radio pulses echoing from deep space, but a time when the universe whispered its secrets through the dim glow of distant nebulae and the raw power of pure mathematical intuition. It was in 1934 that two astronomers, Walter Baade, a German émigré who had sought refuge and scientific freedom in the United States, and Fritz Zwicky, a brilliant and notoriously eccentric Swiss physicist at Caltech, published a paper that would rewrite the very end of stellar evolution. Their work was a breathtaking leap, a vision so radical it would be dismissed and largely ignored by the scientific establishment for decades. They proposed not one, but two astoundingly bold predictions. First, that supernovae, those fleeting cosmic flares of immense brightness, were the cataclysmic death cries of massive stars. And second, that these violent collapses would forge something previously unimaginable, a tiny, city-sized object, composed almost entirely of the newly discovered neutrons. To grasp the sheer audacity of their claim, consider the stellar physics of the time. Stars were understood to burn hydrogen into helium, then heavier elements, sustaining themselves through nuclear fusion. Their death was thought to be a more graceful fading into white dwarfs. But Baade and Zwicky connected the dots between the neutron's existence and the colossal energy output of a supernova. They reasoned that if a star's core ran out of nuclear fuel, its immense gravity would trigger an unstoppable collapse. The energy released by this gravitational implosion, as matter plummeted inwards at staggering speeds, would be enough to power the brightest explosions in the universe. This was a profound balancing of the cosmic books, where the gravitational potential energy of a collapsing star perfectly accounted for the supernova's unfathomable luminosity. Delving deeper into their theoretical construction, Baade and Zwicky envisioned a process known as inverse beta decay, the fundamental particle physics reaction at the core of their hypothesis. In a dying star's heart, under pressures beyond human comprehension, pressures that could crush mountains into atoms and atoms into their constituent parts, electrons would be forced into protons. The electrostatic repulsion that normally kept atoms distinct would be overwhelmed. The electron, instead of orbiting, would effectively be squeezed into the proton, transforming it into a neutron, simultaneously emitting a ghost-like neutrino. This continuous process, where electron capture turns the very fabric of a star's core into a dense, neutron-rich soup, would form what we now call a proto-neutron star. Their insights were purely theoretical, drawn from the elegance of mathematics and the nascent understanding of particle physics. The observational astronomy of the 1930s, with its relatively crude telescopes, simply could not confirm such an exotic object. The notion of a star shrinking from millions of kilometers across to a mere 20 kilometers in diameter, containing the mass of several suns, was beyond the grasp of direct observation. Baade and Zwicky were, in essence, prophets of a new kind of astrophysics, painting a picture of cosmic objects that would remain unseen for generations, theoretical specters waiting for technology to catch up with their genius. Their paper was a theoretical blueprint for the zombie star, an object not accidentally stumbled upon by later generations, but one of the most audacious and spectacular predictions in the entire history of science, a testament to the power of human intellect to foresee the universe's deepest secrets. We have journeyed through the cosmic whispers that first revealed their existence, and delved into the audacious prophecies that foretold their birth. But to truly comprehend the neutron star, we must now plunge into its heart, into a realm where the very laws of matter are rewritten under pressures so profound they defy earthly comprehension. Forget the oft-repeated phrase that a teaspoon of neutron star material would weigh 1 billion tons. While true that monumental mass only hints at the alien physics at play, what does it actually mean to be denser than an atomic nucleus itself? It means traversing layers of matter unlike anything found elsewhere in the known universe, states so extreme they are impossible to replicate in any laboratory on Earth. Our descent begins through the neutron star's thin, solid outer crust. Here, the conditions are perhaps the most familiar, though still intensely exotic. It is a lattice of heavy atomic nuclei, perhaps iron or nickel, tightly packed and held together by the familiar electromagnetic force. Yet, swimming between these nuclei is a sea of highly energetic, relativistic electrons, stripped from their parent atoms by the immense gravitational pull. This layer, though only a few hundred meters thick, experiences pressures thousands of times greater than the center of our own sun, yet it is merely the calm before the storm. As we plunge deeper, past a depth of perhaps 1 kilometer, the pressure intensifies to an unimaginable degree, and we enter the inner crust. This is where matter begins to behave in truly bizarre ways, a region where the nuclei, under such colossal squeeze, are forced to merge and deform, giving rise to what physicists, including the American physicist Charles Horowitz and his collaborators, have aptly dubbed nuclear pasta. Envision atomic nuclei no longer as distinct, spherical entities, but as stretched and elongated structures. As the pressure mounts, they first form long spaghetti-like strands, then transition into gnocchi-like blobs, eventually flattening into sheets reminiscent of lasagna. This isn't mere analogy. These are the predicted shapes of matter, dictated by the delicate, desperate balance between the powerful, short-range, strong nuclear force trying to hold them together and the electromagnetic repulsion striving to tear them apart. It is a cosmic culinary nightmare, a macroscopic manifestation of quantum mechanics. Beyond the inner crust lies the outer core, a vast, uniform ocean of pure neutron fluid, interspersed with a sprinkling of protons and electrons. Here, the density reaches truly mind-bending levels, and the particles exist in an extraordinary state known as superfluidity. This means the neutron fluid flows without any friction or viscosity, moving with an eerie, frictionless perfection. Simultaneously, the protons within this same layer are predicted to become superconducting, allowing electricity to flow with zero resistance. Consider this paradox: a fluid that is frictionless and superconductive, yet existing at temperatures of billions of degrees Celsius. It is a testament to the incredible quantum phenomena that emerge when matter is pushed to its absolute limits, a frictionless maelstrom encased within a star. But the ultimate mystery, and the realm of greatest speculation, resides at the very heart of the neutron star, the inner core. Here, pressures become so extreme, so unfathomable, that even the resilient neutrons themselves may be broken down into their fundamental constituents. Scientists hypothesize that the neutrons, protons, and electrons could dissolve into a swirling, superhot soup of their more fundamental particles, up, down, and potentially even strange quarks. This exotic substance, known as a quark-gluon plasma or strange matter, is a theoretical frontier. Luminaries in the field, such as the brilliant physicist Edward Witten, have championed the idea of stable, strange matter, pondering its profound implications for the universe. While its existence within neutron stars remains a subject of intense research and debate, it highlights that at the very core of these stellar remnants, we might encounter matter so fundamental, so alien, that it challenges our deepest understanding of reality. A neutron star, then, is not merely a uniform, incredibly dense ball of neutrons. Instead, it is a fantastically layered world, a cosmic onion peeling back to reveal increasingly bizarre states of matter. From its rigid, crystalline outer crust to the bizarre nuclear pasta of its inner crust, from the frictionless superfluidity of its outer core to the potentially deconfined quarks of its innermost regions, each layer presents its own unique geology and physics. It is a testament to the raw power of gravity, capable of transforming familiar atoms into structures that push the boundaries of condensed matter physics and quantum chromodynamics, transforming a dead star into a living, albeit incomprehensible, laboratory of extreme physics. After plumbing the crushing depths of a neutron star, exploring its unimaginable internal geology and the bizarre states of matter it harbors, we now turn our gaze outward. For these cosmic remnants, these seemingly dead zombie stars, are not merely objects of passive study. They are, in fact, the most extreme and precise laboratories in the universe, instruments capable of proving the most esoteric theories about space, time, and gravity. In 1974, at the colossal Arecibo Radio Observatory, nestled within a natural sinkhole in the verdant hills of Puerto Rico, a new chapter in astrophysics began to unfold. It was there that Russell Hulse, then a graduate student, and his supervisor Joseph Taylor Jr. made a discovery that would forever change our understanding of the cosmos: a binary pulsar, designated PSRB 1913+16. This was no ordinary isolated pulsar, those lonely cosmic lighthouses we had previously observed, whose rhythmic beats had first hinted at the existence of these strange, dense stars. No, this was a pair of neutron stars, two stellar corpses, locked in a tight, dizzying orbit around each other, one of which was a pulsar, sweeping its precisely timed beams towards Earth like a celestial clock. The discovery sent ripples through the scientific community. Here was a system unlike any other, a unique cosmic dance that offered an unparalleled opportunity. Joseph Taylor Jr. and his colleagues, notably Joel Weisberg, embarked on an extraordinary scientific endeavor. For years, with painstaking precision, they meticulously timed every single pulse from PSRB 1913+16. Each pulse, arriving with phenomenal regularity, was like a tick of an interstellar clock, allowing them to measure the subtle variations caused by the orbital motion of the two neutron stars around their common center of mass. This required an almost superhuman dedication, tracking the celestial clock's every beat over many thousands of orbits. As the years of data accumulated, a profound and undeniable pattern emerged. The orbital period of these two neutron stars was not constant. Instead, it was slowly but inexorably shrinking. The once rock-steady rhythm of their gravitational waltz was subtly accelerating, their orbits drawing closer and closer by mere millimeters each year. Such a minute change might seem insignificant, but in the realm of celestial mechanics, it was a thunderous revelation. The question immediately became, why? What force, what cosmic drain, was siphoning energy from this tightly bound binary system? The answer lay nearly 6 decades earlier, in the mind of Albert Einstein. His revolutionary theory of general relativity, published in 1915, predicted that massive accelerating objects should emit ripples in the very fabric of spacetime itself. These ripples are what we call gravitational waves. Einstein's theory further stipulated that objects losing energy by emitting these waves would see their orbits decay. For decades, gravitational waves remained a theoretical curiosity, an elegant mathematical prediction, but one for which no direct evidence existed. The sheer weakness of these space-time ripples meant that even the most catastrophic cosmic events were thought to produce waves too faint to detect. But here, in the distant dance of these two zombie stars, was the perfect cosmic laboratory. Their immense masses, each comparable to our Sun yet compressed into a sphere no larger than a city, combined with their blistering orbital speed, created conditions extreme enough for gravitational wave emission to be significant. The orbital decay observed by Taylor and his team matched Einstein's predictions with astonishing accuracy. This shrinking orbit was precisely the energy loss expected from the emission of gravitational waves. It was not a direct detection, for that would come another 4 decades later, but it was the first and utterly compelling, indirect evidence for their existence. This groundbreaking confirmation of Einstein's elusive prediction earned Russell Hulse and Joseph Taylor Jr. the Nobel Prize in Physics in 1993. The profound implication cannot be overstated. These dead stars, these remnants of stellar cataclysms, were not merely static objects to be observed. In their intricate gravitational dance, they were actively proving one of the most esoteric and fundamental predictions about the very fabric of the universe. A neutron star, therefore, transforms from a mere subject of study into an active participant in a cosmic experiment, a natural laboratory far more extreme and precise than anything humanity could ever hope to construct on Earth. They became the ultimate cosmic proving ground, demonstrating the universe's adherence to rules that were once purely theoretical, rules that govern the very warp and woof of space-time itself. We are told that the stars are cosmic alchemists, forging the elements that make up our world. But what if the most precious materials, the gold on your finger, the platinum in your car's catalytic converter, could not possibly be created in the fiery hearts of even the largest suns? For decades, scientists faced a profound cosmic mystery. Where did the universe's heaviest elements, those beyond iron on the periodic table, truly come from? Normal stellar nucleosynthesis, the process by which stars fuse lighter elements into heavier ones, could account for everything up to iron. Even the cataclysmic explosions of supernovae, the death throes of massive stars, could produce some elements up to uranium, but never in the quantities observed across the cosmos. This left an enormous gap in our understanding of the universe's chemical inventory. The prevailing hypothesis was that these rarest of elements, including the gleaming gold and the resilient platinum, were forged in environments far more extreme than any single star could offer. It required a crucible of unimaginable power and neutron density. For years, this remained a theoretical concept, an astrophysical placeholder in our models, until a singular event on August 17, 2017, ripped open a new window onto the cosmos. This was not just another observation. It was a groundbreaking multi-messenger astronomical event, dubbed GW 170817, and it marked the first time humanity witnessed the true origin of cosmic treasure. The event began 130 million light-years away, in a galaxy so distant that its light had been traveling towards us since the age of the dinosaurs. It was there that two neutron stars, the ultra-dense remnants we have explored, began their final cataclysmic dance. Listen closely. For millions of years, these stellar corpses had orbited each other, slowly spiraling inward, losing energy through the emission of gravitational waves, those ripples in space-time itself. We know this because it was the first signal to reach us. The twin detectors of the Laser Interferometer Gravitational Wave Observatory, or LIGO, in the United States, alongside the Virgo Interferometer in Italy, simultaneously registered a faint, rising chirp, a perfect symphony of gravitational waves, signaling the last agonizing seconds of these two dying stars. As they spun faster and faster, spiraling closer with each passing millisecond, the gravitational stresses became incomprehensible. In their final moments, the stars were completing hundreds of orbits per second, their surfaces skimming within a mere few kilometers of each other. The ultimate collision was not a gentle embrace, but a violent, hyper-energetic crunch, instantly fusing them into something even more exotic and unstable. This cataclysm unleashed a colossal burst of energy, known as a kilonova, an explosion roughly 1,000 times brighter than a typical nova, but far dimmer than a supernova. It was a cosmic fireball, ejecting vast quantities of superheated, neutron-rich material into the surrounding space at speeds approaching 1/3 the speed of light. And here is where the alchemical magic truly began. Within that ejected debris, under temperatures reaching billions of degrees Celsius and densities that beggar belief, a unique series of nuclear reactions unfolded. This is known as the Rapid Neutron Capture Process, or R process. Picture an environment so overwhelmingly rich in neutrons that atomic nuclei, like iron and nickel, found themselves bombarded by a relentless, rapid-fire fusillade of these subatomic particles. They absorbed neutrons faster than they could decay, building up to incredibly heavy, unstable isotopes. These unstable nuclei then underwent a rapid series of beta decays, transforming their excess neutrons into protons, thereby creating new, stable, and often extremely heavy elements, including gold, platinum, uranium, and countless others. For days, then weeks, after the initial gravitational wave signal, conventional telescopes around the world, from X-ray to radio, observed the fading afterglow of this kilonova. This electromagnetic light was the direct signature of the radioactive decay of these newly forged heavy elements. It was the universe literally glowing with its fresh supply of gold. This singular cosmic event, so distant and so violent, provided irrefutable proof that the most prized materials on Earth, the very substance of your wedding ring, the precious metals vital to our technology and economy, were not born in the placid hearts of suns, but in the spectacular, destructive death throes of these zombie stars. Neutron stars, once seen as mere curiosities, dead relics of a bygone era, were suddenly repositioned. They are not just objects of study, but essential actors in the story of cosmic chemical enrichment, the true alchemists responsible for the universe's most coveted treasures. The cosmos holds countless wonders, objects that challenge our very understanding of reality. Among the already bizarre and extreme family of neutron stars, there exists an even more terrifying incarnation, a cosmic monster whose magnetic fields defy everything we know about the universe, the magnetar. We once believed we understood the limits of stellar remnants, those ultra-dense cores left behind by collapsing stars. But in 1992, two brilliant theoretical physicists, Robert Duncan and Christopher Thompson, dared to propose something far more extreme. They envisioned a special class of neutron star, one not just incredibly dense, but imbued with a magnetic field so colossal it would make even a typical pulsar's formidable field seem like a weak refrigerator magnet. Their calculations suggested fields 1,000 times stronger than those of ordinary pulsars, and an astonishing quadrillion times stronger than Earth's own magnetic field. To truly grasp that scale, consider this: our planet's magnetic field, though vital for life, measures mere tens of microteslas. A magnetar's field, however, can reach hundreds of gigateslas. If a magnetar were as close to us as the moon, every iron atom in your blood would be ripped from your body, and your molecules would simply cease to exist as you know them. How could such an unthinkable force be generated? Scientists hypothesize that these ultra-powerful fields are forged in the first few seconds of a neutron star's life, a fleeting moment of intense, chaotic energy. As the star collapses and its core is compressed into a neutron star, it is spinning incredibly rapidly, perhaps hundreds of times per second. Simultaneously, the interior is still convectively unstable, meaning hot, dense matter is churning violently, much like boiling water. This combination of extreme density, rapid rotation, and turbulent motion creates an incredibly efficient and powerful dynamo effect, twisting and amplifying the nascent magnetic field to truly cosmic proportions. It is a birth of unimaginable violence, unleashing a power that will shape its existence for millions of years. The consequences of such a field are truly bizarre and violent, pushing the very boundaries of physics. This is a field so strong it would distort the electron clouds of atoms, warping their very shape and function. What does this mean for us? It means that chemistry, as we understand it, becomes impossible. The fundamental interactions between atoms, the dance of electrons that forms molecules and powers all life, would simply break down. If you were within thousands of kilometers of a magnetar, its field would literally tear your body apart, not by crushing you, but by ripping the bonds between your atoms, rendering you into nothing more than a cloud of disassociated particles. It is a force that doesn't just crush, it fundamentally rearranges matter. And these are not just theoretical nightmares. On December 27, 2004, the Earth felt the chilling touch of one such cosmic monster. 50,000 light-years away, in the constellation Sagittarius, a magnetar known as SGR 1806-20 experienced what scientists call a starquake. This was not a tremor, but a cataclysmic rupture in its incredibly rigid, super-dense crust, akin to an earthquake, but on an interstellar scale. The energy released by this event was staggering. In a mere tenth of a second, SGR 1806-20 unleashed a gamma-ray burst so powerful that, despite traversing the immense void of 50,000 light-years, it measurably disturbed Earth's ionosphere, effectively rippling through our planet's upper atmosphere. The sheer power of that single, fleeting burst defies human comprehension. It released more energy in that blink of an eye than our Sun, our life-giving star, has emitted in 100,000 years. Magnetars are, without question, the true monsters of the cosmic graveyard. These zombie stars, far from being inert relics, possess immense power that can reach out and affect our planet from across the galaxy. They are astrophysical phenomena that push the known laws of physics to their absolute breaking point, representing a unique and profoundly hazardous force in the universe. The universe, in its relentless pursuit of extremes, pushes the boundaries of our understanding not just with its vastness, but with its very smallest, densest creations. For all we have uncovered about neutron stars, these incredibly compact remnants of colossal stellar deaths, a fundamental question persists: are they truly what they appear to be, or do some of them harbor a secret identity, an even more exotic form of matter hidden beneath their seemingly familiar surfaces? This isn't just an academic debate. It delves into the cutting edge of theoretical physics, where the most extreme objects in the cosmos serve as crucibles for our most fundamental theories of matter and reality itself. We understand that a neutron star can only hold so much mass before collapsing further, presumably into a black hole. This theoretical breaking point is known as the Tolman-Oppenheimer-Volkoff limit, or TOV limit, a celestial threshold beyond which gravity becomes utterly irresistible. Scientists calculate this limit to be roughly 2 to 3 times the mass of our Sun, compressed into a sphere no larger than a city. Exceeding this mass means the star's immense gravity overwhelms even the neutron degeneracy pressure that ordinarily supports it, leading to an inevitable one-way journey into the infinite space-time warp of a black hole. But what happens in the murky, gray area just below this catastrophic limit? Consider the crushing pressures inside the most massive neutron stars, those nearing the TOV limit. We speak of densities where a single teaspoon of material could weigh billions of tons, where atomic nuclei are squashed into bizarre nuclear pasta shapes, and where neutrons form a frictionless superconductive fluid. Yet, even neutrons, seemingly fundamental particles, are themselves composed of something smaller, quarks. So, as the pressure mounts to unimaginable levels in the innermost core, does the very structure of the neutron finally break down? Could the individual neutrons, which are made of up and down quarks, be forced to dissolve, transforming the neutron star into something altogether different? This provocative question leads us to one of astrophysics' most fascinating hypotheses: the existence of quark stars, or strange stars. These are not merely denser versions of neutron stars. They are theorized to be objects composed not of distinct neutrons, but of a stable, macroscopic soup of their constituent quarks, including not just up and down quarks, but also the slightly heavier, strange quarks. This exotic substance, known as strange matter, would represent a completely different state of matter, more fundamental than the neutron itself. The theoretical framework for this audacious idea is deeply rooted in the Standard Model of particle physics, the reigning theory describing the fundamental forces and particles that make up our universe. Visionary minds have explored the profound cosmic implications of stable, strange matter. A key proponent in this field is Edward Witten, a brilliant physicist at MIT who has extensively theorized about the possibility of strange matter existing in a stable, bulk form. If strange matter is indeed the true ground state of matter at extreme densities, then any neutron star that grows massive enough would convert its core, or even its entire being, into a strange quark star. Such a transformation would be a cosmic phase change, as dramatic as water turning into ice, but on a stellar scale, fundamentally altering the star's internal dynamics and ultimate fate. The challenge, however, lies in observation. Distinguishing a quark star from a neutron star proves to be an incredibly difficult task, as from the outside they would appear remarkably similar. Both are incredibly dense, compact objects with powerful gravitational fields and rapid rotation. It is a cosmic game of spot the difference, played across light years, where the telltale signs are subtle and elusive. Scientists are diligently searching for minute differences in their observable properties, such as their cooling rates over millions of years, or perhaps slight variations in their maximum masses before collapsing into black holes. A quark star, for instance, might cool more slowly due to different internal heat transport mechanisms, or it might possess a slightly higher or lower maximum mass depending on the properties of strange matter. And beyond even the strange star hypothesis, the realm of speculation extends further into ideas so audacious they challenge the very notion of what fundamental truly means. This is where the preon star hypothesis emerges, pushing the idea of nested fundamental particles, where even quarks are not the final building blocks of reality. If quarks themselves are composed of even smaller, more fundamental particles called preons, then the extreme pressures within certain stellar remnants might even force these preons to deconfine, creating a star made of something truly beyond our current understanding. This concept, while highly speculative, reminds us that the universe holds mysteries far deeper than we can currently grasp, pushing the boundaries of physics to unimaginable limits. This deep dive into the theoretical frontier serves as a powerful reminder that science is not a collection of settled facts etched in stone. Instead, it is a vibrant, ever-evolving frontier of active investigation, where every new observation and every theoretical breakthrough opens up more questions than answers. The most extreme objects in the universe, like these dense, enigmatic stellar remnants, are not just curiosities, they are ultimate crucibles, cosmic laboratories where our most fundamental theories of matter are tested, stretched, and sometimes entirely rewritten. Beyond the cosmic graveyards where stars meet their fiery end, lies a truth far stranger than mere death. For what if the most extreme and seemingly inert relics of the universe were, in fact, its most profound communicators, constantly broadcasting secrets encoded in their very essence? We have journeyed through the mind-bending physics of neutron stars, those impossibly dense remnants that dwarf atomic nuclei. But to truly grasp their significance, we must now listen to their echoes, the cosmic signals they send across the vast emptiness. These are not just individual objects of scientific curiosity. They are indispensable players in the grand tapestry of the cosmos, providing an unprecedented window into the universe's deepest puzzles. These zombie stars act as an interstellar symphony, their collective impact far exceeding the sum of their individual parts. Their echoes manifest in diverse forms, the exquisitely precise pulses of radiation they emit, the ripples in space-time known as gravitational waves they generate, and the cataclysmic bursts of gamma rays that announce their most violent acts. Each of these signals carries a unique set of information, a message from the heart of cosmic extremes, waiting for humanity to decipher its meaning. Consider the astonishing precision of pulsars, those rapidly spinning neutron stars whose beams sweep past Earth like celestial lighthouses. Their regularity is so profound that they can rival the most accurate atomic clocks ever built, offering a natural laboratory for timing experiments across astronomical distances. This unparalleled cosmic clockwork is not merely a curiosity, it is a vital tool in one of the most ambitious undertakings in modern astrophysics, the search for a galactic-scale gravitational wave background. Collaborations like NanoGrav, the North American Nanohertz Observatory for Gravitational Waves, are meticulously timing an array of pulsars spread across our Milky Way galaxy. Their goal is to detect the incredibly faint, long-wavelength gravitational waves that are theorized to permeate the universe, ripples generated by the titanic mergers of supermassive black holes at the centers of galaxies billions of light-years away. Any slight correlated disruption in the otherwise perfect timing of these multiple pulsars would be the undeniable fingerprint of these grand cosmic waves, a universal hum of space-time itself. Then there is the monumental event of August 17, 2017, known as GW 170817. This was a cosmic epiphany, the first time humanity directly witnessed two neutron stars colliding, a cataclysm that resonated across the universe in two distinct ways. First, the gravitational wave observatories, LIGO and Virgo, detected the final death spiral of the two ultra-dense objects, a rising chirp of space-time as they merged. But crucially, for the first time, telescopes across the electromagnetic spectrum also observed the afterglow of this kilonova explosion, the light emitted as the neutron-rich debris expanded and decayed. The combination of these two signals, gravitational waves and electromagnetic light, provided a completely new, independent method to measure the Hubble constant. This fundamental constant describes the expansion rate of the universe, and its exact value has long been a source of one of cosmology's most pressing debates. The dual observation of GW 170817 offered a crucial new piece of data, akin to finding a missing cornerstone for the entire edifice of cosmic understanding. In essence, these once seemingly dead stars assume multiple, indispensable roles in the cosmic drama. They are cosmic historians, their spin rates and internal temperatures acting as indelible records that chronicle the titanic supernova explosions that birthed them, revealing the conditions of the universe at those moments of creation. They are the universe's most efficient alchemists, responsible for enriching the cosmos with the heaviest elements, like gold, platinum, and uranium. The very wedding ring on a person's finger, or the critical components in our most advanced technology, were forged in the spectacular, destructive death throes of these zombie stars, demonstrating their profound connection to life itself. And perhaps most importantly, they are cosmic messengers, their unique emissions providing unparalleled, real-world laboratories for testing the most fundamental theories of physics, from the intricacies of general relativity to the very nature of matter at its absolute limits. These signals, traveling across vast distances, challenge our current models and push us towards a deeper, more accurate understanding of reality. The final, transformative message of these zombie stars is that these dense and seemingly inert relics are, in fact, among the most dynamic and informative phenomena in the entire universe. By meticulously learning to interpret their echoes, the rhythmic pulses, the space-time ripples, and the powerful bursts they send across the void, we are doing more than just studying dead stars. We are gaining a profound new understanding of the life story of the cosmos itself, from its violent birth to its ongoing evolution, and even to its ultimate, enigmatic fate. The universe continues to speak, and through these cosmic echoes, we are finally learning to listen,